Alright, so today is Kotlin Heroes, and I'm already a bit late, but let's see. So I have my facecam on now because we're allowed to do that now. I've already done the big reveal. I actually don't have a place to put my subscriber count, which is sad, but yeah. So in this contest, basically the only language usable is Kotlin. So, and if you get top 50, you win a t-shirt. So I'm wearing my previous shirt from Kotlin Heroes 4 in celebration of that. And yeah, we're going to try and do well now. So it's probably not going to be as much commentary because I should like try to do well. But I'll go over solutions at the end in a traditional manner if people happen to want that. So let's go. Given two numbers x and y, there's a variable. You can add 1 and you can add x and change it to y. X times 10 to the p. Okay, so try all the largest p's, I guess. Let's see, how does this work? Long ants equals 0. I also have my Java template. Oh yeah, that's probably important to mention. I'm actually writing in Java, and I'm going to be using a transpiler from IntelliJ to convert it to Kotlin, because I don't really know Kotlin, but I do know Java, so that'll be fine. For long z equals a billion, z is greater than 0, z is less, and then we divide z by 10 every time. Then if y minus x times z is greater than 0, greater than equal to 0, y minus equals x times z, plus those ants, because we're trying to do as few operations as possible. Then we add the remainder of y. Alright, bit rusty. That's fine now. I also set up my compilers for Java as well. What? JRun. Whoops. Okay, that's very wrong. What's with that? Oh, while. That would be important too. 4, 5, 20. Yeah, we're going up to a billion. X is at most a billion, so that's all that makes sense. We're good. Could stand to be a bit faster, but that's fine. Setting up with the language I don't really know. Alright, just open all of these. Compilation error. Oh, right. I forgot to do the conversion. Whoops. Okay, so I have also this annoying sort of setup that I have to do, which is a bit unfortunate, but you know, whatever. Am I really not able to get rid of these messages? Can I actually not do that? Okay. Alright, that put us a minute behind. Great. Let's see. Camera is working, right? Mic is working. Everything's good. Audio is good. Let's hope. Okay. RBS deletion. Alright. So we got some bracket sequence stuff. How's that time? 202 milliseconds. Okay. You're given a string. You can choose a prefix. You can choose a non-empty substring. Look at the maximum number of operations you can apply until S becomes empty. The maximum. So I guess every pair we can make, we would want to remove it with the second operation. Every pair inside like this first big grouping we would want to remove, and then how'd this work? Well, we want to like Yeah, we want to like maintain as many of the outer groupings as possible, because like we can split it into a bunch of different regular bracket sequences that are fine. Um, but if we get rid of like the whole one, like if we get rid of 6 with one of these special operations, then that's bad because every prefix operation is forced to remove at least one of these. So, how are we gonna do this? Okay, I guess we can like, let's see. So keep track of the count in, count out equals 0. Int n equals in dot nint. K equals in dot nint. Actually, I don't need these. Can be ints too. String s equals in dot inster. So if s dot char at I is equal to that, if val is equal to 0, then we have like a new group. So minus count in plus count out. Int adds equals 0. If count in is greater than or equal to k, then out.println how does this work? Does it work to print count in and count out? So we have 1, 2, 3, 4. So we get rid of all the inner ones first. And then so if we don't have enough operations, then it's sort of just the number of inner ones plus everything else. Otherwise, we have more operations than we can use, so it should just be everything. Yeah. Let's see. So 2, 3, 4. Seems good. Okay. By the way, this is the best interface ever. It'll auto-detect that I'm trying to like write Java in a Kotlin file, and it'll auto-convert it for me. That's so cool that it does that. Because otherwise I would have to like make a new file and do a bunch of annoying stuff. Okay, let's see. Hopefully this doesn't wrong answer. Alright, 2 policemen. Does it compile error? 2 policemen patrolling a street. The first one is standing at the point. Okay, good. Why does that take so much longer? Wow, that is a long time. Jeez. It's a bit concerning. I guess there's more input though, like 4 5v5 things. Would that have a 2-second time limit? Or 3 seconds. Okay, cool. There's a street that can be represented as an array of length n. There are 2 policemen patrolling it. The first is standing at the point x, and the second is at y. During 1 minute, both policemen can decide what to do. Move left, move right, or do nothing. The street is considered clear if each point of the street is visited by at least 1 policeman. Okay. I guess we can fix the point where they don't cross and then have it be that. Sure, that works. Alright, int n n.nint, x equals n.nint, y equals n.nint. Let's see. Answers at most 10 to the 7th is fine. 10 to the 8th, sure. Okay, so int a equals, we just want x to be smaller than y. So let's see, the midpoint can be anywhere between a and b. No, the first policeman visits inclusive 1m, the second visits exclusive m, or m plus 1 to n. So the total cost is either you go left, you go right, and then you traverse the whole thing. So int cost left equals, I'm really starting to adopt the Java stuff. I'm doing like camel casing now. Let's see, so it's m minus 1, or just m, the total length, plus math.min of the time it would take to go left and the time it would take to go right. So that's example 1. Also, this is m minus 1 actually. So you'd either go from current to m, so for example, say you're at 4, you have 2 minus 1, 4 minus 2. So it's direct subtraction. So m minus 1. Alright, this should be, no, a minus 1, m minus a. Now what is this? So this is n minus m plus 1. So if m is 3, n is 5. So it should actually be n minus m plus math.min n minus b minus m plus 1. Right? Because m minus b, and then just doing small examples out of my head to corroborate things. Yeah. And 6 minus, so 3 and then 7. So then this would be 4 to 7. Yeah, okay. God, I can't type at all. Jeez. Java is indeed quite verbose. That's wrong. Okay. What's with that? Y equals a. Messing something up. M minus m, y. Should be 1 less than that, maybe. It's m minus 1. Well, that doesn't explain everything. Should fix the first thing, but everything else is still messed up. Okay, so 771. Oh. I see. The policemen move independently. Jcomp, jrun. That would make more sense. 235 4012. Okay, right. And the reason is because this should be m minus 1 because we already start off having visited 1. So the interval's length is m minus m, but yeah, we subtract 1 because it's less than that. Everything else seems good. Yeah, okay. And of course it would be less than 2e6. Okay, problem solving marathon. I'm not being fast at all, but that's fine. Wants to solve S problem in n days. Let AI be the number of problems he solves during the ith days. So he wants, I forgot to do that. You can probably won't be able to count on one hand the number of times I'm going to forget to actually convert it to Kotlin. AI is an integer value, sure. AI is greater than 1. Cool. Alright, we're not doing that bad, I guess. Yeah, pretty good. Not the fastest, of course, but pretty good. Am I going against second thread? Oh, he's having fun. I don't know what's with him, but he's having fun. Did he just skip A, or... Alright. So AI is an integer value for all I from 1 to n. AI is greater than or equal to 1. It's non-increasing, so it's reverse sorted. And each thing is within 2 times the next value. Wait, no, it's greater than. So it's sorted, but it's also within 2 times as much. Okay, so we want to give as little as possible to everything else, but we want to give it all to an. Is that the idea? I guess that would be the idea. Maybe we could binary search on the answer. Had to be 10 to the 18th, didn't it? Why would they have to make it 10 to the 18th? Also, s is greater than or equal to n. Wait. What? What are they doing? So the answer is at most s over n, right? That should be the case. The answer is at most like s over n plus 1 or something. Long n equals in dot n long. S equals in dot n long. S over n plus 3. And we can figure out the lower and the higher bounds we can get. And we can get any number in between just because, like, arguments. I don't have my writing tablet with me, so let me just grab that really quick. Or the pen that goes with it. Okay, whatever, it's fine. I'll code it first and then think later. So the absolute maximum, or the absolute minimum on the answer is... No, the absolute maximum. What? Now I'm confused. So the minimum we can get is around O2S. So I guess we don't really need it to be, we don't need it to fit, we just need it to be S. Long m equals okay, so let's see, have this be long. So plus equals cur. We have to be ceiling. Cur equals cur plus 1 over 2. Has to be ceiling. Yes. So now if cur is equal to 1, then everything else we get is going to be 1. So if we're at position I, for example, 0, then if we're at position 1, n is 3, or n is 4, then we get 4 minus 1 minus 1 left. Count plus equals n minus I minus 1, break. If count is greater than or equal to So if count is greater than s, we have to go lower. Oh wait, this should be m. Count is greater than or equal to s, then it's too high, we have to go lower, right? So r is m, else l equals m plus 1. The answer should be either 15, 5, and 5. What? Oh wait, also this should be s plus 1 because it's exclusive. I'm not actually sure how that worked. That should not have worked, but what? 16 r equals m. Now I'm confused. Why would that be? Okay, so 12, 12, 14, 14, 15, 15. Oh, we have to do minus 1. Because this is the lowest value that works. So if it works, we're going 1 higher, otherwise we're going low. So if it works, we're going to be too high. Wait, what? If count is greater than s, then set it to that. This feels like it's some weird off by 1 error. J run 1, 100, 100. Why would that be 2? Wait, why is that 2? 1, 100. So we have 2 values. We check if this works. If it doesn't work, then we go there. I see. So why would that be 2? I don't understand. It's stopping at 1. Why would it go to 2 now? Let's make a bit of a stronger test. So let's do like 5. So let's do like, let's see. So we have 2 days for make that 1, and then we'll make that this. Well, actually, all I really want is 100, 100. What? Oh, I didn't recompile it, did I? Oh, that makes sense. Okay. Do this strong test now. Okay, 6666666, etc. is right. That is right. That should be 1. Have one more. Should be 8 now. Okay, yep. It's 15, 4, 4. That should be 1. Should all be good. Okay, perfect. So it doesn't seem like it overflows at the very least. That's the idea. So once again, we're making sure this is fine. Count plus equals m minus I minus 1. Because everything else is 0. But we include I, so we're excluding I. So it's the interval n minus I plus 1. Then we subtract 2 because reasons. No, it's n minus I plus 1. No, it's n. That's the number of elements in it. Yeah, okay. That is right. Okay. And r equals s plus 1, and everything is good. We should not overflow because we're only going down. Famous last words. I need to convert. Hopefully the audio is still working. Yeah, okay. I'm just a bit paranoid now. Don't want my sudden face cam to break everything. Nope, wrong problem. Palindromic doubles is a scary name. Okay, subsequence is a sequence that can be obtained from another sequence by removing some elements. Yep. Palindromic sequence is a sequence that's equal to the reverse of itself. Longest palindromic subsequence of sequence A. What? Why? Any integer value appears no more than twice. Okay. So that does matter. What is happening? All right, so for example, there would be 5, there would be 4. We're supposed to make a segment tree or something? Okay, perfect. How are we doing on speed? Alright, similar position, sure. Right answer on test 2, okay. Subsequence is a sequence, right. And we could build a segment tree, do it like that. Multiple things named after doges. Okay. Could build a segment tree. Are we supposed to do that? Is that what this is supposed to be? We figure out the longest subsequence starting here. Either this is the end, so this is the midpoint, or this is not the end, or maybe it is the end. So we say that we're going to include its pair, and then we have to only take things that are to the right of its pair. So we need a segment tree for that. Yeah, why not? Okay. Well, I have a segment tree written in Java already, so that's cool. Code. Let me see if I remember how to use it. Don't need lazy. Let's see. So that's gonna make this pretty easy, I would hope. So, come on, mouse. I believe in you. You can select some text. Okay, so how's this gonna work? We have an n, we have an int n, we have an array. int n equals in.nint. I'm not sure why that is messed up. Alright, we want longs because that's how I did everything. Because I was edgy back then when I wrote this template. So AI equals in.nlong. Alright, so segtree n. Alright. Now okay, so we can say minus minus AI. Pause I is equal to -1. Actually, I don't need longs at all. That's fine. Okay, so for an I equals n minus 1, I is greater than or equal to 0, I minus minus. Oh, yeah. If pause I is not equal to -1, then other AI is equal to pause I. Otherwise, you can also have other be -1. So if this current position is not -1, then we set the other to that. Otherwise, pause I is equal to I. Right. This was C++. There would be a better way to do this using vectors, but let's just ignore that. So if this position is not -1, then we set the other. Or if we have a previous occurrence, then we set the other occurrence to that. Otherwise, yeah. Okay, so now we consider this element first. Let's see. So this would be st.query. How does this work? I just have it be indices. Yeah. So one single equals 0. If I is less than n minus 1, single equals st.query I plus 1 to n minus 1. Combine. We already do maximum. That's actually perfect. Ants equals math.max ants single plus 1. Can't call a variable double, so we'll dub. I don't know. So if pause I is not equal, no, other AI is not equal to -1, and this is not the other, so this is the first occurrence, so it can't be equal to this index, then we'll say long dub equals 0, and if other AI is less than n minus 1, dub equals st.query other AI plus 1 n minus 1. Then it should be dub plus 2. Then we update the segment tree to account for this position. And we don't have to worry about updating the same location twice because it's fine. So we set this position to, we set other AI to the value double plus 2, because that's the new length of the sequence we get. And because we're iterating through the array in increasing order, we already know the left side is handled. We just need to handle the right side. And that's what the segment tree is for. Int. That does not work. Okay. So, yeah, dot println other AI. Oh, because that should be, yep, okay. There's a very low probability of working like that. I'm not sure what's what. 5, 4, 1, 2, 3. Okay. So let's make sure this seems legit. So we read in the array, we create a segment tree. We create other and pause arrays, initialize them both to -1. Now we go backwards through the array, and then in the first occurrence, which would be this case, we set the position to this, and in the second occurrence, which would be this case, we set the other value to the first occurrence. And there are at most 2 occurrences, so that's fine. Now, we start off with an answer for each thing. We first consider it alone, so this would be if this is the middle. And to do that, we simply query everything to the right of it. So that would be st.query I plus 1 and minus 1. Indeed it would, everything to the right of it. And then we add 1 because that's a possibility. We include this in the sequence. Now, if other AI is not equal to -1 and it's not equal to I, meaning this is the first occurrence and there are 2 of them, then we consider it taking both. So it's any sequence to the right of it that's more than it, we add 2, and then we update to correspond to the sequence we're going to make. Seems legit. Okay. Hopefully time is fine. Don't expect, I didn't convert that either. Damn. I'm gonna get more compilers than actual submissions. You guys want to bet I'll have more compilation errors than actual submissions? Or accepted submissions, let's say. Because there probably could be some more non-accepted submissions. Alright, so we get rid of internal for both the things. Then it should work. Yeah. We don't have any comparable issues. I know having comparable is sort of weird too. It like puts a question mark even though it shouldn't, but it doesn't seem like it'd be a problem right now. Got it? Alright. That puts us in a better spot now. We are in 8th. Nice. So I guess as the problems get harder, it'll be easier to like do some stuff. Alright. Guess other people are doing well. Okay. Recently, cryptocurrencies have become increasingly popular, and decided it was about time she started mining the Dogecoin cryptocurrency. They do like Doge. They had Doge forces too, and that was a really annoying problem. So hopefully this isn't. There are forecasts of the cost of 1 Dogecoin. Every day Anne can sell any amount of Dogecoin. She mined it on the 8th day, and she can sell it on the same day. What? Why? First and last days of mining. Okay, so we need stuff there. What's the maximum profit? Oh, okay. So basically every time we get an interval, I really should find my pen. Like where did this go? Did I just lose it on the floor or something and it disappeared into the void? Oh, yeah, okay. Into the void of my bed. Sure. So we have this array. Now I can finally open Paint. So we have this array like I don't know why it's stuck on this size. We have this array like 4, 1, 2, 3, 2. Every time we get +1 to our current total, and the optimal position for this is going to be the largest position to the right of it, which also could be itself. So for example, if this is the full array, we'll want to sell this here. We'll want to sell this at the 3. We'll also want to sell this at the 3 and this one at itself, and then we'll sell this one at itself. So we're looking for the largest position to the right of anything, or to the left of anything. So in some cases that's not possible. So I presume we do some magic with a monotonic stack, but I guess we'll see. Yeah, that seems legit. Okay, so what we're going to do first is we're going to sort by queries. So we don't need a segment tree anymore. Actually, wait, yes we do. We need a segment tree with lazy prop this time. So that's cool. And I need a max query. No, I need a sum query. Let's see, this can be long now, because why not? So am I allowed to make an array of array lists? I remember not being able to do that. I don't know why they wouldn't allow that, but I guess that's fine. I can do 2 pointers. Or 8 pointer. So you read in the array. Static class query. Let's see. So we need L, R, and index. Wait, what? Messed that all up. L equals LV, R equals RV, I equals IV. So query. Am I allowed to do this? I should, right? Make arrays of objects. Okay, good. I know maybe there was a problem with like arrays of array lists or something, but I don't know what it was. There was some issue. I know Java has issues. Maybe it is better to use Kotlin because it doesn't have as many issues, but you know, whatever. We're already deep in the rabbit hole now. So, magic for int I equals 0, I is to none, I plus plus, out.print res I plus space. That would be the plan. Alright, let's do magic now. So that was not, it's kind of anticlimactic. So we're going to maintain a stack of indices is the idea. Yeah, alright. stack integer how does this work? Java stack push. I can just do shouldn't be on Geeks for Geeks, but okay, stack is fine. This works, right? Okay. For int r equals 0, r is less than 9, r plus plus. Actually, let's do better. Let's just make a virtual stack. Because that way we can access before, which is sort of what I need. So wait, is this fine? I guess it will be fine, right? Like we compare the current element to the current top. It's just sort of annoying. Let's do this. So all right, int targ equals r. So while while true, because Java doesn't have this. So also we need segtree make it of n. How does this work? Okay, we can initialize it with an empty array. Yeah, sure. Alright, cool. Let's see, st.update rr ar while true. So int v equals stack s point. All right, so if AR is greater than AV, then we remove V from the stack, minus. Actually, this should be targ. So if, actually it should be R, I guess. Don't know when we need a targ. So if AR is greater than AV, then we remove V from the stack, essentially. So minus s point. Int pos equal to 0. If s point is greater than 0, pos equals s point, no, stack s point minus 1 plus 1. Right, so if we have some other element in the stack, then make it only up to that interval, otherwise do the whole thing. All right, that's the plan. Int v is stack s point. Wait, should be minus 1. Yeah. So the previous element in the stack, if this is greater, we remove it, then we kill its whole interval. We kill its whole family, basically. You're actually just gonna kill its whole family. Okay, so st.update. It's from position to last, and the value is AR minus AV. We're gonna update the range to make it so it's all equal to AV. And also the strategy here is that every moment the element in the segment tree corresponds to the greatest element, like to the right of it, that's within the query interval. And we're sweeping the query interval right. That's the idea. So then what we do is else break. What we do is last is equal to, what would this be? Pause. -1. Yes, if the current position is here, that's what we updated, so now we have to go further. Okay, cool. Now, I also need a Q point. So while Q point is less than Q, and should sort these, QV Q point dot R is equal to the current R, then plus Q point. Res QV Q point dot I st dot query QV Q point dot L QV Q point dot R. Okay, now for into I equals 0 as in Q. Minus L minus R. QV I equals new query LRI. So while this R is equal to exactly this, set the res to the query and that. Okay. Now sort arrays, collections, I guess. No, it should be arrays. Well, with object arrays, it uses merge sort, right? So that should be fine. Actually, it should be arrays. I don't trust Java. Maybe Kotlin fixes this, but it uses objects, right? Merge sort for arrays of objects. Yeah, okay, we're good. Well, if you're wondering where I learned Java from, this is like the language we learned in school for the longest time. And also, like, other competitive programming contests force us to use Java, so I do know how to use this. I think. Int compare to query other, return R minus other dot R. So this is less, it'll return a value less than 1. If it's greater, it'll return a value greater than 1. And if it's equal, it'll be that. This can be int. Okay. If it works first try, I'll be very surprised. Doesn't even finish reading the input. Alright, reading the array, reading the queries. S point is 0. Where am I breaking? Out.println. I have a feeling it's on the first loop, but who knows? Oh, it is. Yeah, it's on the first loop with the 4. Have we handled the queries already? No. So breaking here. Why are we breaking here? I'm having some issues with this. So while s point is greater than 0, if s point is already greater than 0, then... Oh, wait, shoot. I didn't even put anything onto the stack. That makes sense. So s point plus plus is equal to r. Yes. Okay, that doesn't make any sense, but... Wait, is this still reading input? What is happening? What is it doing? Oh, it still thinks I'm using test cases. Oh my god. Wait, is this the first one where you didn't have test cases? Guess it must be, huh? Wait, I mean E. Yeah, they all had test cases before. Okay, I guess that makes sense. Alright, that is weird. I don't know how that got through the full input. That would make sense why it's still trying to read stuff. Array index out of bounds exception. 85 should be Q. At least it doesn't crash anywhere else though. 15982. Okay. Let's make some random stronger tests. So like 10. 1. 6. Make it a permutation. I don't have queries. Let's see. 7. Why not? Still printing indices, right? What am I printing? Wait, what am I printing? Oh. Actually, a better way to test this would be to just look at what it has every query at every point. So 1, 6. So 8 plus 3 times 9, 27, 35, plus 38. No, plus, wait, 35 plus 12, 47. Oh, this can go to 9 too. Okay, so that works. 110 should be, everything here should go to 9, 36, everything here should go to 8. So 17 times 4, 68, and then we get 2 7s, so 82, yep. This should be 24 because duh, this should be, what is this? So 18 plus 30, 34, yep. This should be 2 5, this should be 30. This should be 7 9, 17 looks right, 4 8. So 9, 2 6s, 21, then 2 of those. Wait, 9 plus 6 plus 6, 21. No, 9 plus 4 8s, which is 41. Okay. Actually, an easier thing to do is just to test this. So for int I equals 0, I less than n, I plus plus, out.print, st.query, I plus space, out.println. Just doing this because I want to avoid wrong answers, and if I have to debug, I'm going to have to debug anyway. Oh, that's not what I meant to do. So let's see. 885, 852, 9999, 993, yep. 4, 8, 8 takes over everything, 1, 7. Perfect. And we'll check the same thing here. So 4, 4, 1, 4, 2, 2, 4, 3, 3, 3. Yep, looks perfect. Okay. Make sure we got rid of all the debug prints now. 15982. Okay. Seems good. Let's get rid of all the internal clauses. Get rid of all the weird stuff. They do like their... Okay, so get rid of internal, because it really doesn't like that. Get rid of that, and then get rid of that. I guess that works. This is just all my stuff for messing with Kotlin. Okay, you have painting numbers. You have n numbers, each integer is, you have a, what? You have a bunch of distinct numbers. Paint them red and blue. Okay. That's not the best time, but we're fine. Yeah. I mean, there's no hacking or anything, so. Cool. Still an 8th. Interesting. Not the fastest, but interesting. Yeah. You're given n integers, each integer is from 1 to n. All of them are pairwise distinct. You have to paint them red and blue. The cost of painting is the number of pairs x, y, such that y mod x is 0, y is red, and x is blue. For each k, calculate the maximum cost of exactly k integer should have a red color. Cool. That is very cool. If exactly k integer should have a red color. So it's the number of its divisors, right? Y mod x is 0, y is red, and x is blue. Don't think I understand. Why don't we just paint the smallest ones red? Do they have sample explanations? They don't. Oh, maximum. Okay, okay. Maximum. I see. Nice. All right, so it's equivalent to saying for each blue one, we get the number of its multiples, right? So we can sort of go backwards. Say that we have to have a certain number of blue ones. Yeah, I'll be right back. I need to go to the bathroom. Think about this in the meantime. Remember to mute my mic and then unmute it after. Oh, it did not press stop recording though. That's bad. Apparently I gotta text them. I don't know if that's like meaningful or if it's just... Is it spam? Yeah, it's spam. Okay, cool. In that case, make sure the mic's working. I would hope so. Okay. So we're gonna do some stuff. Let's see. Long n equals in dot n long. So I conjecture, and by conjecture I mean guess, that primes can't hurt us. And let's see. So the optimal strategy here for 11. First we put it in 1. Then we put it in 2 or something. And then 2 would give us +4 and then subtract 3. And then we can put it in 3. And 3 would give us +3 and subtract 1. Is that how that works? Wait. What are they doing? So 1, 2, and 3. 3 would give us... Oh, okay. Yeah. That seems good. Okay. So long res equals new long n. Res 0 equals 0. 4 into I m minus I minus 1. Minus 1. Okay. Alright. Long count equals new long n. Long boolean used equals new boolean n. So now 4 int I equals 0, I is less than n, I plus plus. Actually, I equals 1, I is less than or equal to n. So if count I is less than or equal to 1, so if it's either a prime or it's 1, then long cur equals 0. Long mult equals 0. 4 int j equals 2 times I. J is less than or equal to n. J plus plus. Mult plus equals plus plus mult. Plus plus count j. Tot plus equals mult minus count I. Used I equals true. So I don't even think we need that. We should not need that. Yeah. So res tot plus plus is equal to something. Actually, wait, is that even optimal? Do we want to go by primes? It could be better to... Actually, yeah. Wait. What? Might not be optimal to go by primes. Might instead be better to do something else. Like, what if we use 4 instead of 5? What would that give us? In some optimal configuration, we use all the divisors before a number anyway. So we have some sort of like topological sort. Okay, maybe it's not optimal to do that. Could it be? If we have 4, for example, and some huge n, it's better than using a prime. Yeah. Okay, so greedy doesn't hurt because in the optimal strategy, we're going to use all the divisors of a number before we actually use that number. So therefore, the order in which we pick things doesn't really matter. And costs are decreasing. Okay, yes, that works. Because costs are decreasing. Okay, so we don't. It's a bit more involved. We want to use a priority queue or something. So count I is equal to n over I. First, that works perfectly. Then priority. Does this work? Java priority queue. It does. Okay. Alright, so I remember I had this for a reason. I had a pair class because this should work. Okay. How to do this? So it was pairs. Actually, I don't need this. Let's just write a separate thing. Don't need segment tree anymore. Get rid of this. Oh god. I don't know what that was. Okay, so static class element long val int pq equals new priority queue. So public L God, I cannot type end equals I. Okay, so pq.insert new L count I. Int tote equals 0. Long cur equals 0. Alright, so that should be -1. Okay, so we're going to simulate deletions by just doing stuff. So while tote is less than n-1, Lx equals pq dot what's the element? What do we need to do? Just give me the poll. Okay. Poll. All right. I remember poll is cool because it actually removes it too. If x.val is not equal to count. So if we determine that this has to be at a lower benefit, then we can't use it because this is a higher benefit. So if x.val is not equal to the count of x.int, or we've already used it, continue. Otherwise, cur plus equals x.val. This is n log squared, also not the best. but I guess that's fine. Let's see. Res plus plus tote is equal to cur. Then for int I equals 2 times x dot ind. Alright, also used x dot ind equals 1. I is less than or equal to n, I plus plus, minus minus count, I, pq dot insert new l, count I. God damn. Alright, 11 errors. I guess we don't need n to be long. Okay, what? So, an int, sure. What is it? Push? What do you want? I don't know the syntax. Does that reduce the number of errors? It does not. Okay. What do I have to do? Add? It's add, isn't it? Yeah, it's add. So every language, everything does it differently. Okay, so int, fine. Hate that it makes you do this. Anything else? You happy now? Used, oh wait, yeah, that, fine. That I'll accept because it doesn't like booleans like that. Okay. Oh. So let's see, if val is less than other dot val, return -1. If val is greater than other dot val, return 1, return 0. Okay, that, something is up with that. So out.println x.val plus that plus x.ind. Why is what? X.val. So somehow this is 4. I guess because it's arbitrary, but priority queue sorts by val is less than other dot val. Wait, am I supposed to? How does this work? It's like almost right. Does it work here? I mean, I imagine it wouldn't, but okay. What? Why would it do that? Why is it? If val is greater than other dot val. Is it a max heap or a min heap? I don't understand. No. Okay, that's not helpful. I guess it must be a max heap, or a min heap, I guess. Sure. So what's happening? Here we're gonna have 4 and 6, right? Is that how that works? And 4 gets those two, 6 gets those. So something's messed up. Why does 5 have -2? Oh. Okay. That is the mistake. It should only be multiples. 3, 6, 9. Yeah, okay. Cool. Alright, that would be an issue. Yeah. So long res, long count, boolean used. Alright. So for each, set its count initially. Right. Int tot long cur. Well, for n-1 times, element x is equal to the poll. Then if it doesn't work, then continue. Otherwise, add it to the current answer. Then set that current answer to this. Then make it used so that we can't revisit it. And then decrement all of its multiples. Cool. Works for that, right? What am I printing? Oh. It's hard to locate print statements. In C++, like you have the double angle brackets, so it's so easy to find debug prints, but here it's just not possible. Kotlin. Yes, Kotlin. It is Kotlin. Code in Kotlin, of course. What other language would it be? Okay, get rid of internal, get rid of internal, get rid of the question mark. Guess we're good. Alright, so given a integer n and a sequence, it is a string problem. It has 10 second. It has a 10-second time limit. All of these have high time limits now. My God. Okay. All right. You're given an integer n and a sequence a of n-1 integers. Each element is either 0 or 1. You're asked to build a string. Each letter is one of 4 possible ones. If ai is 1, then the ith suffix of the string is lexicographically smaller than the i+1 suffix. Okay, what is happening now? Is it TLE? It might TLE. That is possible. It is n log squared. That would not be the best. Could have done with a higher time limit on this, but I guess we'll see. It's running very slowly. Test 6. Test 8. Just hope it doesn't TLE. So I should probably check my messages at some point. That would not be a bad idea. Okay, it's getting through a test a second. So I guess it's fine. Actually, I could have tested it on custom invocation. That would not have been a hard thing. But if we're at 26 tests, it probably passes, so we're good. Alright, if ai is equal to 1, then the ith suffix of the string is lexicographically smaller than the i+1 suffix. If ai equals 0, and the ith suffix of the string is lexicographically greater. How is it not passed yet? There's so many tests for whatever reason. Okay, there we go. 904 milliseconds. Alright, I guess that's fine. So my signature is so bad that that's the constant it has. Alright, we've dropped to 10th. That's cool. Still going very strong. Not many have solved H yet, so I guess that's the next target. Interesting. Were this a contest, what would this be? It'd be like 2,900. Nice. Cool. All right. 3 problems left. That is a lot of stuff. Okay. So flip the value of AI. If AI is 0, then set AI to 1 and vice versa. After each query, print the number of different strings that satisfy the different constraints. Given constraints. So this is lexicographically greater than the suffix. So if they're the same, how would that work? If we say this has to be lexicographically greater. If it's a tie, then spaces are treated as like -1. So it would mean that if the smaller string would be default to lexicographically smaller if they're the same. Is it possible for the answer to be 0? 10 seconds also. My god. Why would that even be? Are we supposed to build like a segment tree over DP or stuff? That would not be fun. I would not enjoy doing that in Java. Because we're using Java and not Kotlin. Yeah. Alright, it's working, right? Just getting my... Yeah, okay. So... So if it has to be lexicographically smaller, then it could be the same. Right? It could theoretically be the same. Because, like, if we stick on some character, so... Either... So I guess, say we have some string like, for example, like B, A, C, D. So we want this to be lexicographically smaller. So say we stick on A, then it's perfect. If we stick on C or D, then it's not going to work. If we stick on B, what happens? That's sort of the bigger thing. So this is lexicographically smaller if and only if the how'd this work? It's like if and only if the characters themselves are Let's see what the 10-second time limit is for now. Maybe we are supposed to build a segment tree over DP values. Oh, why would they make us do this? So we're interested in this character. And if it can be the same or not. So what we want to do is, we look for the next character that's different. If this character is... So first there's the possibility that no characters are different. In which case... we're... Like, there's nothing that happens. Actually, we can stick on a space character at the end that sort of symbolizes that. Okay, so that works fine. Cool. So then we say, if this is less, if this next character is less, then what happens is we automatically, what happens? So putting this on will make it lexicographically greater, so we can't. And otherwise, if this is greater, for example, this is C, then putting this on will make it sort of like shifts, like the position which they differ is here in this string and here in this string. So this is sort of like the comparison point. So if this is less than this, if this B is less than this C, then we win. Okay. Alright, so I guess this is some sort of segment tree stuff on DP values, or like a matrix or something annoying. Do I have to do this to get top 50? That's my question right now. Do I have to do this? Like, this is just not, this is not fun. Why would they make this a problem? Second third is barely clutching. Although I suppose he's had some trouble with D, but I guess he'll bounce back. His D might have just been really long, so it would have taken a while. That's a reference, not a... Okay, anyway. So first we're gonna just do some stuff. We're gonna start by doing stuff. And the stuff we do is this. So I'm gonna code the naive DP just to make sure it works, and then I'll fix it with a segment tree. So n equals in.init, q equals in.init, int a equals new int n minus 1. Alright, now minus 1. Okay. Alright, this has to be 1. Then, alright, so int, wait. So the mod is 998244353. 998244353, right? Yes. Okay. So DP of 0, where the last character is 0 and 0 is 1. So for int I is 0, I is less than n, I plus plus. For int j is 0, j is less than n. Okay, so if dpij is greater than 0, otherwise it's pointless. Actually, that doesn't matter. I'm gonna have to do that anyway. It's just for testing. So if next this is so annoying. It's actually so annoying. So like we build a transition matrix, and we combine them. So it's like it's 10 to the 5th times 125 times why did it give me that? Log 10 to the 5th. That's the idea. Log 2. Doesn't seem that bad, but when you consider that it's Kotlin. But we also have 10 seconds, so maybe that'll work. Is that really what we're supposed to do, though? I mean, my god. People solving this? Like, I really just want to see if there's an excuse for me to not have to do this. And I guess they are. Well, people did this in 20 minutes. That's insane. That's actually insane. Alright. So if AI is equal to 0, okay, so if AI is 0, that means it has to be less, right? Greater, okay. So let's start with 1. So then next, so we're gonna put this on if A is 1, then if next, so this has to be less. So if next is less than J, that's the thing we get, then dp I plus 1 next J plus equals dp I J K. Else if next is equal to J, if K is less than next, no, next is less than K, dp I plus 1 next, no, it's J and then K because it doesn't change, plus equals dp I J K. So this should be in reverse, right? Yeah, m minus I minus 1. 0. Okay, perfect. Oh, alright, so now we flip all these, so if next is greater, then, yeah, okay. What? Oh, and read the... Should be 10 though, so that is concerning. Why'd it be 10? Start off with a blank character. Now this must be greater than that. Oh, that'll be why. JRun. Okay, there we go. So, int x equals in.init a x minus 1. Does that work in Java? That'd be cool if it did. Cool. Alright, now this should be 6 and 10. Oh, it's because it's interleaving. Okay, cool. So now we have to do this with a matrix. We have to do it with a freaking segment tree, because this isn't gonna pass. Because this in itself is NQ times 125, which is absolutely horrendous. So we have to make this with a segment tree. And I'm gonna save this in another file, just in case. Open a new window. Main.java. Okay, perfect. Now we're gonna do some segment tree stuff. So we don't need a lazy segment tree, which is cool. Okay, so static class matrix. Int a5, no, long a5. So this works for small cases. It would basically work for everything, right? That's just gotta be how it goes. Int v. Why does this lag so much? A equals new long 5. Rather, this can be a long v, I guess. So if so I guess this is the thing. So if v is equal to 1, I really don't get what is causing this to lag so much. Am I running a program? What's happening? Okay. I don't know what's happening, but cool. Alright, so basically what this means is it's like a transition matrix, right? So how does this work? Wait. Oh god. It's not that simple, is it? It's not that simple. It's not that simple. Because the second tree would be 25 cubed. That's not gonna happen. Right? 25 times 25 cubed times log 225. That's not gonna happen. What's the status on H? Like how long are people taking? People are TLing 8 seconds. 2 seconds. 6 seconds. Oh my god. Wow. 99.83 milliseconds. People are TLing, I suppose. Yeah. Are they testing it, or are they actually like having problems with it? I can't believe that ran in 9.9 17 milliseconds left. That's insane. I'm pretty sure top 50 is secure right now because not many people are going to solve this, but it's worth a shot. It's worth trying. For my own sake. But like also like pain. And a lot of pain. So that would suck. And in fact, it does suck. So there's a transition from one state to another. How bad is this? How big is 25 cubed? It's like literally... It's gonna be worse than O of NQ. That's how it is. It's gonna be worse than O of NQ. We can optimize multiplication, but that's not the problem. I mean, the problem is that it's no matter what, it's not going to be fast enough, right? Is that the problem? We're actually supposed to do 25 cubed. I don't believe that. I guess technically it's 20 cubed, but what difference does that make? How many states are actually reachable? We're getting to this point. So, everything can be with that. So we have OO. We have star O. How does this work? We have OO, we have star O. What else is happening? Okay, what are the actual visitable states? So we can have O, we can have anything of the form that and O. We can have 1 and 2, 3, and 4. So this is 5, this is 3. So we get 17 in total. So how bad is that? 17 cubed. It's not much better. Times log 2 of 1e5. It's like literally NQ. There's no way this is ever gonna pass. Unless. Is there a better way to do transitions? Is there a better way to do stuff? I don't know. It can't hurt to try, but it also can. I'm assuming he's gonna TLE too. Jeez. Another person got 9983? Seriously? Yeah, he's definitely gonna TLE. Okay. So, whatever's happening is not good. What's the memory? So 25 squared times 25. Okay, memory is fine, right? Times 25 times. I just try and save the web page. 8. Oh, that is a problem too. Okay, both memory and time are a problem. 17 times 25 times 4 times 8. No way. Okay. Alright, this is not the smart way to go. Is there a smarter DP we can do? Is there a better way we can figure this out? I mean, probably. Just don't know how. I guess we can store them as ints, but that's not going to help. People are getting close to the memory limit too. Yeah, they are. Somehow this guy has a very nice solution. So does him. So does he. Anyone else? Anyone else trying? Like, I know I should try, but I also kind of just don't want to. Is it necessary to do this to save my rank? Quite sure it's just not necessary. Flip the value of AI. Obviously, I can't submit the DP, but I mean, 17 squared will barely pass the memory limit if I make it ints instead of longs. 17 squared. Are either of these other problems worth it? Probably not. The people who have solved H have not solved this yet, so it's probably not doable. boundaries. Wow, so we're supposed to solve this in O of n times something. So I guess this one's optimized knapsack somehow. Has anyone done this? Oh, even Tourist hasn't done it, so I guess that's not gonna happen. Seems like this is the best I'll do. You're not submitting for this. Wait, where's geothermals? Oh, he got it a while ago. Okay. Is there anything else I can do? I can say that do we need the extra state? I feel like we just don't. Maybe we just don't need the extra state at all. So that gives us 12 squared times 1e5 times 8 times 4, which is still unbelievably close, but actually make it ints. So that will pass. It does exist. Is this gonna work? I'm kinda interested. Will this even improve my rank at all if I solve this now? If I solve this an hour and 20 in, if I solve it 2 hours in, it's not even gonna improve my rank, is it? Oh, he got it. Okay. I just solve it for the sake of solving it. 12 cubed times log 1e5 times 1e5. It's not the best, it's also not the worst. Also, he's insanely close, yeah. Alright, it seems like this is the way to go, though. So wait, let's try better. So 4, 4. Wait, 16 squared times 25 times 16. That's not great. I mean, it's 2 billion though. This is not the worst. Does this still work? What's the problem? Am I not closing this right somehow? Where's the problem? Oh, is it that? What? Oh, okay, fine. I'll just comment it out for now. So this still work if I have these transitions. Array index out of bounds exception 2. Where? 60. Oh. Still? Where? Oh. Oh, and 4. Okay. Why? Because I didn't actually do it. Yep. Let's fix the starting character. Okay. Still works as expected. Alright, so that is my pane now. So now we need a 16 by 16 transition matrix. I don't know what that was for. Why did I replace the whole thing? I just need to replace this part. And I comment. Nice. Alright, so this is 12 and 12. No, 16 and 16. So this is like, this row relies on that column. So if we were to have a column matrix and multiply it by this, if we were to have a row matrix, and this would multiply by that, this multiply by that. So it's like this row relies on this column. So plus plus A on J times 4 plus K, next times 4 plus J. Or it's, now it's the opposite. Right. This row relies on this column. Okay, now plus plus A, J times 4 plus K, J times 4 plus K. And this is the same thing. And this is the same thing. Okay, sure. Now we make a new one, matrix A. Alright, now this should be int. Perfect. Now, I should not screw this up. Matrix. Sure. So this is 16, 16, 16. I don't care about indentation. It's gonna look like a mess, but whatever. So what is this? Now, vals I j plus equals vals, no. So it's CIK, because we're doing it reverse, times 1L times B dot A. So this should be public. B dot A of K and J. If vals ij is greater than or equal to mod vals ij minus equals mod. Aij equals int vals ij mod. Okay, so this is a matrix now. It's an array of matrices. New matrix AB. If b dot a 0, 0 is equal to -1, return C. If sure. If v is equal to -1, okay. see. So it should be m.a 4. What is this? So 0, 5 times I, 5 times I. This is not going to work first try, but I can attempt it anyway. What? This indentation is so messed up. Okay, that's what it is. God. Alright, let's see. So, we're gonna combine them. Yeah. Okay. So what? Alright, so 4. Oh, if v is equal to 1. Copy this. C.A ij. Change this to C. Change this to B. Otherwise, do the matrix stuff. So it doesn't like that. Doesn't like that. This should be a matrix. How many errors does that fix? 1 error. New matrix. It's not like it's gonna work. 04. That is surprisingly close. Oh, 04. Wait, what? What is it? Okay. Next times 4 plus j. Next j, alright, jk. So swapping these will make a difference. No. So what we want is we want the number of ways to actually wait. Should be like also be sure to might be that. Okay. It does it in the wrong order. unfortunate. So what's happening? Should be swapped. Actually, it doesn't make much sense, but maybe the whole matrix is inverted by accident. Okay, now. Alright. This is the best we got. Well, I'm not sure what's up with that. So, right? So we update there and there. What if I swap these? It still dies. 5 times I. If I swap both of them. It's gotta be something, right? Keep messing with things until it works. Is that the... That would be the plan. Does that actually work? Wait up, okay. Alright, yeah, equals 0. Can't believe that worked. Alright, so how bad is this? Oh wait, Java. Okay. Should probably test it in Kotlin. No pointer exception. Okay, whatever. Maybe I'm forcing it to read input while it really can't. Okay, but it doesn't really matter because we have like a very short amount of time left, so we might as well just submit this and hope and pray. I don't know what caused that to break though. It's kind of weird that that did break. If it gets TLE, we'll optimize as much as we can. So this part should be fine. It's run once. This part's the bottleneck for sure. We got rid of the mod. There's not that much better we can do. We're sort of forced to have all these states, aren't we? Guess we'll find out. does like to take a while on my submissions for some reason. Do we MLE? Is that also possible? The garbage collector will kill that array. I mean, it shouldn't MLE, but who knows? So it's 4 times 99999 times 16 squared times 4. So it should be fine. Should be fine memory-wise. Problem would be time-wise. Does it pass test 6? If it gets past test 6, we are probably good. If it hangs, then we're screwed. Alright. That's not a good sign. There's a chance we're just screwed. Is there anything else I can do to optimize this? I mean, I'm using the right mod, right? Yeah. Or so I would think. Alright, it's not gonna pass. Well, with TLE, maybe that's what happens. RIP. Okay. Well, that's over. Gets incredibly close to the memory limit, but... Alright, that was not worth my time. Maybe there's a better way to do this that doesn't involve some, like, disgusting matrix stuff, but I don't really know how to do that. So... I'll leave it as is. What did we end up with? 14th. Okay. That is better than my last rank. So, my last rank was 18th, and this is better. So, that's good. Wow. You got 3rd? Jesus. That's insane. Legend of Kotlin. Alright, have other people done? Second thread managed to save it. Nice. Yeah. H, unfortunate. Was the fastest of A to G, though, at the very least. So, that's not bad. Okay. I will go over the solutions to the problems I did solve, because that was sort of what my promise. So, let's do that now. I'll do it like more briefly because it's sort of less of a thing. So we have a value, for example, 1337, and we have another value x. And what we can do is we can subtract from this new value any power of 10 multiplied by the value of x. And what we want to do is we want to make this value equal to 0. Or you can add to a variable until it becomes this. Those are equivalent. So, and we can do that, or we can just simply subtract 1. Both of these count as one operation. We want to do as few operations as possible to be able to get it to 0. So the basic idea is, like, this is coin change, basically. And the greedy algorithm works for coin change because, like, for example, the numbers we can make with this are like 25, 250, 2500, etc. Right? And this is a multiple of this, and this is a multiple of this. Meaning that if we subtract this 10 times, it's equivalent to subtracting this once, but for fewer operations. So we're allowed to do greedy here because these are all multiples of the previous ones. So basically what we do is we try the largest power of 10 possible. For example, we could try 10 to the 9th times 25. And then we subtract that from 1337, or we subtract that from our input as many times as possible until the input is smaller and we can't do any more subtractions. Then we try 10 to the 8th times 25. We try 10 to the 7th times 25. etc., until we get to, like, for example, itself, 10 to 0 times 25. And then the final number we get after doing all the subtractions is the remaining number of operations we have to do. If we subtract everything and we still get x, then the answer is x plus the number of operations we did here. So essentially coin change greedy. That's the idea. For B, you get bracket sequences, and essentially you're given a regular bracket sequence, for example, like this. And a regular bracket sequence is defined in the problem, so I won't go too deep into it. But basically, this regular bracket sequence, what you can do is, one, you can pick some subarray and delete it, or you can pick some prefix and delete it. However, you can only do the subarray operation at most k times. And you want to figure out the maximum number of operations in total, both subarray and these, that you can do while keeping the array, or keeping the string like non-empty. So you want to do as many operations as possible where you have to delete at least one character each time, and figure out the maximum. So basically the idea is, like, when we have some prefix that's also a regular bracket sequence, then the number of left is equal to the number of right. And this is like sort of a subproblem on its own, and so is this. These are totally independent of each other. We can't remove a subarray that contains these two, because if we did, then like it wouldn't be regular. So yeah, essentially every time we remove a prefix, because we can only remove a regular bracket sequence, we have to remove one of these groups and the entirety of one of these groups. Because if we removed only part of it, then it wouldn't be regular anymore. So essentially the prefix operation is gonna force us to remove these groups. So say we figure out we have like k groups or something. And we can do this by going through, and whenever the number of left is equal to the number of right, that's a new group we have. So within these groups, every prefix operation is going to force us to remove at least one of these. So let's say exactly one, because removing more than one is pointless. So then with the other operations, with the subarray removals, what we want to do is keep all of these groups in the array. Because if we didn't, then we would remove at least one of the prefix operations that we were doing, and we would make it so we would do fewer operations in the end. So that's bad. So say, like, for example, we could have some internal pairs inside these groups, which is just the number of left and right brackets, right? So each operation with the subarray, we can remove exactly one of these pairs instead of removing an entire group. And then that way, when we remove these, like now we have these sort of like implicit parentheses here, then we can remove as many of these internal things as we can, and that way either we run out of internal things, in which case we have too many of these operations anyway, and so no matter what we do, we get like the best case scenario, that if we run out of internal things, then every prefix operation, or every operation, will delete exactly one pair. So the answer would actually just be n over 2, but so basically, like, we count the number of these internal pairs now, the ones that we're able to remove with the subarray operation, but not with the prefix operation. And then for each of these internal pairs, what we do is we check like let the number of prefix operations be k, and let the number of internal pairs be I. Then basically the casework is, if I is greater than or equal to k, then we use the k operations to remove as many of these pairs as possible without disrupting the blocks as a whole. And then And then each prefix operation will be forced to remove a block. So the answer would be k, the number of internal pairs, plus the number of blocks. And otherwise, if I is less than k, then we're going to have more subarray operations by the time we remove all the internal pairs. So we're really going to have a final string that looks like this, where every single pair is a block. And we have to remove all this with the prefix operations, and every internal pair uses exactly one move. So we get all the internal pairs, and we get all the blocks. Right, but this is actually just n over 2, because every pair in the string takes its own operation. So if we have too few subarray operations, then the answer is the number of internal things we can remove plus the number of blocks, and otherwise we remove the entire string like this. So that's the idea. Guess I can go over h too. I mean, it's like, I don't know. Maybe I'll constant optimize this later. It's not really worth it now. So this is this is this. This is this, indeed. So we have a line, and we have two policemen on that line. Let's say, for example, red and blue. What we want to do is these, in 1 second, each policeman can move left or right or just do nothing. And basically we want to make it so in the end, every position in the street will have been visited at least once. So maybe it's better to draw it like this. So for example, this will be here, and this will be here. Now these policemen can move, for example, in 2 seconds this can go here, in 2 seconds this guy can go here, and then here, and then here, and then, for example, here, and then here. So this takes 4 seconds overall, and after 4 seconds, every position will have been visited by at least one of the police officers. So that's our goal. We want to figure out the minimum number of seconds it takes to do that. So the idea here is we basically assume we have a left police officer and a right police officer. Then if the police officers ever cross each other, they're doing something wrong, because this starts off on the left and this starts off on the right. So it's easier for this police officer to visit all the left points, and it's easier for this one to visit all the right points. So we can assume they'll never cross. And another way to think about it is we'll assume there's some barrier between them, where the red guy can never cross this barrier, and the blue guy can never cross this barrier. So now we're solving two independent problems. The red guy has to fill this whole thing, and the blue guy has to fill this whole thing. So taking that into account, the answer then would be the maximum of the time it takes for these two guys to do their independent things. Right, so now we don't really know what this barrier is, but n is 10 to the 6th, and the maximum number of the sum of n is also 10 to the 6th, and the sum of n being 10 to the 6th implies that we can have some sort of O of n solution. So the way we can do this is we can simply brute force the barrier. We can try all possible barriers and solve each of these individual problems, and then we take the best one over all of them. So now we just have to solve for an individual barrier, for a single barrier, and then we take the best over all of them. So the red guy has to fill in this whole area, and the blue guy has to fill in this whole area. So basically the optimal path is either the red will go to the left and then to the right, or he'll go to the right and then to the left. Because if they ever take some other path, like some other weird path that, for example, goes like this, then they're just wasting time. So really there are only two possibilities. Go here and then here, or go here and then here. And both of these have a very simple cost. This is simply this distance plus this distance, and this is simply this distance plus this distance. So we can take the minimum of these two, and then that's the cost for this police officer. And similarly for the blue one, we can try both of these and both of these, figure out what these distances are, and then take the minimum of them and that gives us the answer for the blue one. Then because both police officers like move independently, the answer for this barrier then is the maximum of the answers for the two. It's whichever one will take longer. And then we take the minimum over all of them. So basically we just do some math with indexing and figure out how long they're going to move at each point, to the left or to the right. If you want the exact numbers, you can see my code. Alright, this one's fun-ish, kind of, I don't know. So basically we have two numbers, n and s. Let's let n equals 3 and s equals 10, for example. So basically we have an array, we have an empty array with 3 positions, or with n positions. Note that n is 10 to the 18th, so it's not an input. We have to create this array. And we want to create an array such that first it's sorted. So every element is less than or equal to the next one. Second, every element is within 2 of the previous one. So what that means is like this can't be more than 2 times larger than the previous one. So for example, to constrain this, if this is AI, then it has to be greater than or equal to AI minus 1. But it also has to be less than or equal than 2 times AI minus 1. Yeah. And so now we're going to... So that's the constraint. So this 3 can't be here. For example, this can be 2, this can be 3, or it can be 2, or it can be 4. But then... Sanity check. But then... Yeah. So what we want to do is... Also, the constraint is that the sum of the elements must equal s. So 1 plus 2 plus 4 equals 7, so this is invalid. But one array we could have is, for example, 2, 3, and 5. Now what we want to do is, over all possible arrays, we want to maximize the last element. Okay. So say we know what this last element is. Then we can sort of figure out the minimum and the maximum values of the array that we can have. So for example, say we fix that the last element is 5. Then if we reverse the condition ai minus 1, a sub I minus 1 is less than or equal to a sub I, less than or equal to 2 times a sub I minus 1, then we get that this has to be phone call. It says scam likely, so that's probably not a good sign. So if we now determine this element from this one, then ai has to be less than or equal to a sub I plus 1. And it has to be greater than or equal to the ceiling value of ai plus 1 over 2. So for example, this ceiling is 3. It's ceiling of 5 over 2. If it was floor, then this would be allowed to be 2, which is not possible, because 2 times this has to be greater than or equal to that. So that's sort of like the definition of ceiling. So basically, this can be any element between 3 and 5. And this can be any element between... So if this is 3, then this is allowed to be 2. And if this is 5, then this is allowed to be 5. So this can be any element between 2 and 5. And it's sort of like a... Let's see, how would I explain this? It's sort of like... It should be intuitive that, like, because we can, like, change the array by decreasing at most 1 element and keeping the array still valid, which therefore decreases the total sum by 1, it should be, like, at least somewhat intuitive that we can get, as a total sum, every value between the minimum possible and the maximum possible. And this is also 5 to 5 because it's fixed. And the proof involves just, like, saying that, like, for every possible array, you can decrease exactly 1 element while keeping the rest of the array valid. Like, for example, if we start with all 5s, then we just decrease all of these, then we decrease everything here to 4. then we decrease everything here to 3. And we decrease them in right to left order. So that way, like, no matter what, the conditions aren't invalidated. And then we decrease them to 3. And then now we've hit this element's limit, so now we can only decrease the first element, and we decrease that until we get its limit. Or actually, we decrease this whole prefix, and so on. And that would be the strategy we get to get any possible sum. But basically, now we know we can get any possible sum. So an ending value is valid only if like the minimum sum is like S is between the minimum and the maximum, because we can get anything in between the minimum and the maximum. So we want to find the largest S where this is possible. So since we know the minimum is less than or equal to the maximum, and we know that there's at least one valid array that satisfies it, because that's they guarantee that. And we know that there's at least one valid array. Really, the only thing we're worried about is the minimum, because we're choosing the largest possible. We're choosing the largest possible, like, if we say min is a function of x and max is a function of x, or the like y or something, where y is the supposed final element we take, then we're going to maximize y, meaning that this is going to be as large as we can possibly make it, and so is this. So really, like, because the distribution exists, because there's always a way to do it, the maximum possible sum we can have that where the minimum doesn't exceed s will always be greater, or greater than or equal to s. So really all we need is for a minimum of y, the minimum for a given value y, like the minimum sum we can make, to be less than or equal to s. And the minimum is something we can compute in O of log n. I'll get to that in a second. So really, this is something we can binary search on. We can binary search on the optimal value of y, the largest y, such that this still holds. So the way we can compute this value is simply like, so we know the last value is going to be s. Then the second last value is going to be as small as it possibly can, which is ceiling of s over 2. Then the next smallest value is going to be the ceiling of s over 2, etc. Right? So this value is going to decrease by or it's going to like decrease by around 2 every time. For example, if we have 10, then this goes to 5, then this goes to 3, then this goes to 2, then this goes to 1. And when we hit 1, we know that we can't go any farther. So really, like, if this is x, then we have, if we use x elements in the initial stage, then we have n minus x ones. So really the answer is like the sum of these, or the answer for the minimum is the sum of these plus the remaining number of ones we have. And whenever we hit a 1, we know everything else is going to be a 1, so we can stop. Yeah, so basically we just naively compute the last few elements. And make sure also that when you have n elements, you stop. Like if n is 3, then you can't have 4, so you just stop at 3. Yeah, so that's the plan. Basically, we do that, we binary search, and it's going to work. And this is going to work in log n iterations because, like, if we think about it in binary, then, like, for example, 10 is that. So if this value is even, then it simply just cuts off the final bit, which divides it by 2. And if it's odd, for example, say we have 11, then it's going to, like, add 1 here, but it's still most of the time going to decrease the length of the bit string. So, like, basically every time it's going to, almost every time it's going to at least halve the value, or get something that's very close to having the value. So this ceiling stuff will terminate in log n, which means the total complexity is log n for the binary search times log n to compute the stuff So it's log squared n per test case times the number of test cases, which is like 1,000, so we're fine. And also note that the minimum value is like O of s. I think it's like around 2s or something, maybe a bit larger, but or around like 2s plus n. So it shouldn't overflow. That's what I'm saying. 10 to the 18th, it's not that bad. It's not really going to overflow. Okay, now we get to the more convoluted ones. So we have E, which is, we have an array of values. Each value appears at most twice, which is an important constraint. Basically what we want to do is we want to pick a palindromic subsequence. So for example, if we pick this, then we say this is going to be here, then the subsequence has to be a palindrome. We want to find the maximum length of a palindromic subsequence. So the way we can do that is, for example, we can say, let's say for each element, let's find the longest palindromic subsequence where this is the middle. So what that means is we have to inherit some subsequence from the left and some subsequence from the right, where this is equal to the reverse of this. So this whole thing must be palindromic, and then this must be in the middle of it. So if we process the elements in from left to right, then we're already guaranteed that this is to the left. But for example, if we're processing, say we aren't processing that. Say we're processing this element instead. Then we have to make sure that we don't have some subsequence that starts over here or ends over here. So basically, like, what we're asking is, for a given value, over all things to the right of it, what's the longest palindromic subsequence that we've found so far? And what's the length of it? And then with this value, we can extend it by 1. Or, yeah, in this case by 1. And we may also potentially add another pair to the subsequence, like so. But that's a different case. So for example, here, we're interested in, over here, what's the longest palindromic subsequence we've seen so far? So it's like a query on, it's like a range maximum query, that's kind of interesting, on a suffix of an array. Now if we consider the other case, well, how do we know what palindromic subsequences we found? For example, say we're going to attach this pair into it. Now there's nothing to the right, so this is length 0 initially. Now we have length 2 because we have this as a pair. And so now essentially we know that we have a palindromic subsequence that where this is to the left, so that's fine. And then like the how do I put this? The leftmost element that's on the right is here. So if we were to extend something else, we would have to extend it from this region. So we know we have a palindromic subsequence of length 2 that can be extended starting from this position. So really it's like saying we update this position to be 2. And then when we do the RMQ, we're basically going to say that, like, for example, this would be 2. So then we know that using this 1, we can extend this subsequence of length 2 because we have a 2 to the right of it. So that's the idea. We're just converting this to a segment tree problem. Basically, for each element, first we consider it being the middle. So for example, here. Then we can extend any subsequence that's to the right of it. So for example, this would be, we'd have this 2 over here, and we would have nothing else. So then we can extend this subsequence of length 2, and then have this be of length 3. And then we can't extend this any further because we already have this being an odd element. Or we can extend an entire pair at once. So we can say we're going to attach this 1 to its pair. Then we can once again extend any subsequence to the right of the right value. To the right of the value to the right. And then, so this would, for example, be 2. So then we gain 2 when we add this pair in. So now we have 4 here, and then we update this index to have 4, because now we can extend a sequence from this index to have 4. And then we continue on, and then eventually we would be here. This doesn't have a pair, so we don't consider that, but we can say that this will extend some subsequence over here, and this is 5. And then we continue. So we ignore everything to the, or we can consider this being the, middle again. We might want to do that, but if something is second in its pair, we don't consider adding it to the left, because then that sort of screws with our condition of like the left and right. So basically we only update the segment tree for the pairs, for the values that are on the left of the pair. And then this is unpaired, so we only consider the first case. This is paired, but it's to the right, so we only consider the first case. And yeah, so basically it's just the segment tree problem, where every point we update we update at the position of its pair the longest subsequence we can have, where this is like the leftmost point on the right. And then when we're here, we consider extending some subsequence sets to the right of it, and possibly updating that too. Note this only works because every value appears no more than twice. So yeah. Alright, for this problem, basically, this is an educational one about answering queries offline. Basically, I'll give the basic rundown that doesn't involve this statement. Basically, we have an array. We're going to query some ranges. For each element, we let its value be the largest element to the right of it that's also on the subarray. So for example, if I had a 7 here, it wouldn't be relevant because it's not on the subarray. So this value would be the largest element to the right of it, which is 3. This would be 3, and this would be 3. And we want to sum these values on that range. So this is once again a segment tree problem. And the way this works is we're going to store a segment tree that has the values of each index. Or rather, we're going to sweep left to right. We're going to answer queries offline. And we're going to say, for example, for a fixed right endpoint of the query, note that like for a fixed right endpoint, every value is predetermined based on this right endpoint. Like for example, this value would be 4, this value would be 3, this value would be 3, and this value would be 3. And this is because the values don't depend on elements to the left. So if we fix the right endpoint, then for all queries that have this as the right endpoint, we can simply do a range sum query on whatever like the interval is. Because we don't care about what's on the left, we only care about the fact that like everything on the rightmost element is this. So really we just need to figure out a way to efficiently compute the values while we sweep to the right. So now the way we can do that is we can say, for example, we can say that each element is sort of going to dominate some range of the array. Let me get a better example. So 2, let's see, I'll make this 5, 4, and 3, and 7. Okay. So every element is going to dominate some range of the array. Then what happens is, so for example, when this is the rightmost element, then we have that this is 5. And so 5 dominates itself, and we're all good. Now, when this 1 is the rightmost element, this 1 is going to dominate itself because it's the only possible candidate, like maximum value. But it's not going to be larger than 5. So everything to the right, everything to the left of this 5 is going to ignore this 1. So then we remove that and we continue. Now this 2 is going to dominate itself. And it's also bigger than this 1. So everything that's dominated by this 1 is now dominated by this 2. So basically, like, whatever range this is dominated by this 1. We set the entirety of it to 2, because now 2 is the largest element that's relevant to it. So we can do that with simply like a range set query or a range add query, whichever you prefer to do. Now, when this 4 becomes the largest element, 4 must dominate itself. It dominates the 2, and it dominates the 2. So wait, the ranges we have so far are this and this. So when we get this 4, it's going to dominate this 4, and it's going to dominate this 2 because 4 is bigger than 2. So the 4 sort of inherits this range, because now everything is contingent on the 4. So first we set this to 4, then we set everything on this range from 2 up to 4. This is equivalent to either adding 2 or just setting the whole thing to 4. That may be easier to have like a set thing, but it doesn't really matter. Now we move the right end to here, and we say 2 is going to dominate itself and nothing else. We move the right end to here now. We say 3 is going to dominate itself and 2, and the range dominated by 2. So for example, this would be 3, and we would set this to 3. And now we get 7, this powerhouse of an element. And it dominates the entire array because it's the largest. So 7 dominates itself, and it dominates that, and it dominates that, and it dominates that. So all of these ranges are gone, and I made this very hard for me to erase apparently. So now this whole thing is dominated by 7. So 7 like eats up all of these ranges into a single one. So note that at every point, the ranges we have are decreasing, because if we ever had some range like this, for example, decreasing and then 1 was bigger, then this would be bigger than whatever this is. So this would eat this range up and it would sort of flatten it out, because all of these would now be dominated by this green. So we have a monotonic array of decreasing values. So we can basically maintain a stack of indices, and then while this is dominant over the top of the stack, pop the stack, we do like the range update, and then we continue on with the stack. And then whenever we hit a point that's larger, for example, say we had an 8, then we would stop because the 7 is no longer relevant to everything to the right. So that's the idea. And then for every write point, for all queries that end at this write point, we simply answer all of those queries. So if we were here, we would answer this using the current state of the segment tree. If we were here, we would answer like these queries and whatever. And yeah, that's the idea. So this works in log n because at every stage we add at most 1 segment to the stack, and we may or may not remove some, but we never like look at more than what's necessary. So we do O of n stack operations and O of n segment tree operations. So the total complexity is n log n. Drinking water. Yep, okay, this is where we get to the point where I like don't have as much proof for things, but whatever. So we have some number n. We have some number n, and essentially we have all the numbers 1 to n like in a line or something, however you want to think about it. We can paint these numbers either red or blue, and the value of an array is, for example, say we do this. The value of an array is the sum over, for each of the red values, it's the number of its divisors that are blue. And this would include itself, but itself is red, so that's pointless. So for example, this 4 has a value of 2 because the number of its divisors that are blue is 2. It has 2 and 1. And this 5 has a blue divisor of 1. So basically, we're given that we can paint at most we have to paint exactly k integers red, and everything else needs to be blue. So we're interested in what's the maximum total value of the array for each possible k, from 0 to, or from 1 to n. Because if k is 0, it's trivial. It's just 0. So what? Why is that not going away? Okay, I don't know what that was. Alright, so first of all, if we think about it a bit, it actually does become easier to solve it sort of backwards, where we say that we start off with n red values, and we're going to gradually change some of them to blue. And the reason that's nice, actually I'm not sure if it's necessary to do that, but the reason that's nice is because now we have like multiples instead of divisors, and it's easier to just figure things out. So basically, now we consider this. What's the cost of changing an element from red to blue? Or what's the change to the total sum of the array? So for example, say we change this element. Now, say we change this element to blue. Now this element used to be red. What that means is that like for every red-blue pair that this formed, we now lose those pairs. So that's part of the cost. We lose that. But now this element is blue. So for every red-blue pair that's now created by changing this element to blue, for example, this, we gain that. So for example, if these two used to be blue, we would lose these two. These two happen to be red, so we don't actually lose anything. And in fact, all that happens is we gain this red-blue pair. Yeah, so the cost is basically that. It's the number of pairs we gain minus the number of pairs we lose, and that's how much changing this value from red to blue would get. So for example, this, we would gain 5 pairs if we change this here. We would gain 2 pairs if we change this here. We would gain 1 pair if we change this. We would gain 0, 0, and 0. Now my claim is that greedy works. We take the largest element, we figure out how that changes all the costs, and we keep doing that for each thing. So what happens when we update the costs? Basically, like, I'm gonna have to prove this, and it is provable. I do know the proof. It's just like sort of annoying to do. So the reason greedy works is because basically, let's figure out the cost first. So when we change this to blue, now it's going to update some of the costs of some of the other ones. Specifically, everything that now gains a red-blue pair from this is going to lose it when we change it to blue. So every multiple of this element now has their like cost decreased by 1, because changing this element to blue would in turn destroy the pair that we just created. So this becomes 1, this becomes 0, this becomes -1, -1, and -1. So 1, 0, -1, -1, -1. Right. So that's not what I wanted to do. Okay. So basically it's going to decrease it from all of its multiples. Actually, wait, how does this work? Is that a correct claim? Yes, it is. Right. So that's how these costs work. So now the other claim that makes the greedy work is that for every value, if we haven't taken some of its divisors, then we're going to take the divisor first. And the reason is as follows. First, you may ask, if we take this divisor first, then that's going to make this cost worse because now we have this new pair that we would lose when we gain this. But if we consider like the long run, sort of, or actually even just the short run, so we may lose a pair in the long term, which is bad because taking this divisor before this might make the cost lower for this. But if we consider it in reverse, if we take this, then we don't get this pair. We don't get this pair, and this has strictly fewer multiples than this divisor, for example. So the divisor is going to have an easier time making pairs than this. And specifically, every pair that would be made by this would also be made by this divisor, and possibly more. So the divisor, like, it gains this. If we take this instead of its divisor, then this pair that we would have gotten had we changed the divisor to blue instead would be lost now. It would never have been made because we just made this blue and like screwed it. We screwed it out of the pair. So that's the idea. Basically, it's always better to take, like, we can show if some element has a divisor that hasn't been changed to blue yet, then it's better to take that divisor than to take this element. And also note that, once again, because this has strictly fewer multiples, the cost of taking this is going to be lower than the cost of taking this. So basically what we get is, we get sort of a DAG, a directed acyclic graph, of the things that we can create, or of the things that we can currently take blue at the moment. So for example, we can always take 1. We can take 2 only if we've already taken all of its divisors. So we can take 2 only if we've taken 1. And we can take 3 only if we've taken 1. And we can take 5 only if we've taken 1. Now for 4 has the divisors of 2. Actually, wait. There's a better way to draw this. For 4, its divisors are 2 and 1. So now we can only take this. We can only take this 4 if its divisors have already been taken. And 6 has all 3 of these as divisors. So yeah. So we get this DAG. And now the answer we're going to get is the order we do the blue things in is going to be a topological sort on this DAG, because we have to take every element that's a divisor of it before we take the element itself, just because we showed that that's optimal. The other part, and the reason this greedy works, is because every edge goes from a larger value to a smaller value. Meaning that at every point, there's no possible case where, like, say this is like 4 and this is 5, but this is 100 or something, and these two are 100. There's no case that, like, if we would gain 5 from this, it's not as good to take this 5, because later on we could take this 4 and then later on get a 100 out of it. So it would be better to take the 4. It would be better to take the 4 and the 100 instead of the 5 and the 4. But that's not possible because the costs are decreasing, or like non-increasing. So a later number is always going to be, at most, like, it won't be better than an earlier number. So there's no case where greedily taking the largest number will screw us over in the future, because all the future values are worse off than this one. So that's the argument, that we can always greedily take stuff from this DAG. Now, the other part is complexity. So we can maintain the, like, current minimum using a priority queue where every element stores, like, where every element in the priority queue is the value in the index. I'll leave the implementation of that to you if it's something you enjoy. And if we decrease the cost, either we can remove it from the priority queue, or we can add a check where this is like, if this value is equal to the cost. Because if it's not, then it's greater, and that means that this was like an earlier element that we haven't updated and we should have deleted. What the hell happened? It means that, like, if this value is greater than the current cost we have for this element, then it means that, like, we should have deleted this, but we didn't because there's no way to delete from a priority queue, it seems. So it means that we do have a different entry that has the updated cost. So we'll sort of just ignore it. So if the value in the priority queue is not equal to the current cost of the index, then we ignore it. That's how we can simulate deletions. And also we can store a separate visit array. I'm not sure if that's necessary. I think it might be. I don't know. The point is that this case is not possible. Also, the number of divisors of a number is O of n log. The total number of multiples over all numbers from 1 to n is O of n log n. I have a blog that proves that, so I will link that in the description if you're interested, as always. And yeah. So that's the basic idea. And then for every time we update the cost, we have to insert a new entry into the priority queue, but there are at most O of n log n entries in total. So really, we have O of n times log squared of n complexity. And apparently this is fast enough. Runs in like less than a second. So that's fine. Yeah. So H is like some stuff that's going on that I don't really know how to do. And my solution may just like be not intended at all. Because some people were having a really hard time with the time limit. And I did too. My solution got TLE. Which is unfortunate. But basically the idea was like you make a DP occurrence, for example, like this. Where DP of I and J is the answer for a string that's like the first unique character is I, and then maybe you have a bunch of I's, and then the next unique character is J. And that's the answer for that. Then the transition is sticking a new character on. Either it's the same character in which the new state is still DP of I and J, or it's some other character K, and it's only possible if like you have to check things. But now the new state is DP and K and I. And then convert it to matrix form and then do some like spooky, because there are 16 states. So it's some spooky like 16 cubed times log of n times q, because you put like matrices on a segment tree and do stuff like that. So it's horrible, but yeah. It is indeed horrible. And then the memory it uses is 16 squared times n, which is like, both of these are so tight, and it may be possible to squeeze my solution in. It seems like other people have succeeded in squeezing some sort of matrix thing in. But yeah, I don't know. That was my idea. I'm not sure if it works. Converting it to matrix form is an experience that I'll let you have for yourself. It's not that hard, really. You just like you put the transitions into matrix stuff. It's like, for example, this is just saying like you basically just copy the DP occurrence and saying like this relies on this and this relies on this and etc. I don't entirely understand how matrices work, so I mean I don't like have the best grasp on them, so I would not be the best person to explain the actual occurrence. But yeah, that's A to H. I didn't even read I or J, so some people have gotten TLE. Yeah, TLE. Unfortunate. Yeah, congrats to Danny for getting third. That's insane. Actually winning money from this stuff. Alright, I have nothing more. If you want my setup, if you want my Java template, it'll also be in the description. And this is just IntelliJ. Like it has a J to K thing. It's like if you paste Java code into a Kotlin file, I think it'll ask you if you can convert it to Kotlin, and then it'll do that for you, and that's like really cool. I'm not sure if that's a default setting. I don't remember since I set this up over a year ago. But yeah, I'm sure it's not that hard to figure out. Anyway, cool. Hope you enjoyed. Goodbye.